Until now, I mean in chapter 3, when you needed to add vectors, forces, for example, you didn't have any trouble because you were dealing just with one dimension. So you either algebraically added the magnitude of the forces or subtracted depending on the question that you were being asked. But in 2D, you have to pay attention to more detail, namely where the forces are pointing at. In some situations, you may not need to decompose the forces. You just use the value, the whole magnitude of the force. In some other situations, you will need to decompose the forces. How would you know if you have to decompose or not? It will all depend on the referential that you pick, okay? And the idea of picking a referential, first of all, you need to know that there is no absolute referential. You can pick a referential like this or like this. As long as they keep perpendicular, they don't need to be, but you are using only referentials whose axes are perpendicular to each other, okay? And if you pick the right referential, you are minimizing the number of forces that you need to decompose, hence speeding up the process of getting the result that you need for that particular question or problem. Let's see one particular example. You have now this box going up the ramp. I'm not worried at this moment about the mechanics of what's going on. I'm just worried about how to represent these forces, okay? And you have this force F that is along the inclination of the ramp. You can imagine this like a rope and someone just pulling the box up, doesn't matter, okay? And what other forces do you have? You have the weight of the box pointing down, okay? If you have a ramp like this, the earth is underneath, the ground is underneath, so the FG always points in the direction of the center of the earth. So in this case, it will be down. And then you have a very important force, which is the normal contact force, the contact force between the box and the ramp. And as the name suggests, is normal to the surface on which the box is laying down. This surface has this inclination, so normal to this means making a 90-degree angle, so it is like that. This is very important. This normal contact force is always perpendicular to the surface of contact of the object and the ground, okay? And the ground or whatever the surface is. So in this case, it's like this. So the idea is, what referential do you pick? If you look at this, you have two options. The idea, again, is to minimize the number of forces that you need to decompose. If you pick a referential like this, y-axis, x-axis, the weight would be on top of the y-axis, right? So there is nothing to decompose there. But the other two forces, the normal contact force and the force F, as you can see, they are not on top of the y-axis, they are not on top of the x-axis, so you need to decompose both. You have two forces to decompose. What is the alternative? Putting the x-axis along the inclination of the ramp and the y-axis perpendicular to it. See? What is the advantage? Now, the normal contact force is going to be on top of the y-axis, and this force F is going to be on top of the x-axis. So there is nothing to decompose on both the normal contact force and the force F. Instead, you will have the weight, the Fg, the force of gravity, which is pointing down, that is not going to be on any of these. So you'll have to decompose this one. See the logic here? It's either decomposing two forces or decomposing just one. So for the sake of simplifying procedures, I would pick, and most of the situations, you will see every time you have ramps, the referential, the x-axis as being along the ramp and the y-axis as being perpendicular to it. Now the question is, how do you decompose this knowing the inclination of the ramp? A little bit of trigonometry, okay? You have this angle over here, theta. There are many different ways to getting this outcome, this result. You have this angle over here, theta, right? The angle is always going to be this one over here, which is the one that the weight makes with the y-axis. How do you know? One way for you to know this. Imagine a continuation of this horizontal line and this one. You can see here a rectangle triangle, right? I hope that you can just continue this line. This one goes down. You have, let me use this marker. You have here a rectangle, triangle. I hope that you can see, right? This being a rectangle, triangle, this angle over here is 90 degrees. So this one is what? Is 90 minus theta, right? The whole thing needs to be equal to 180, right? So this one is 90 minus theta. And what is this angle over here? This angle is going to be this one over here, right? This inclination is this. This vertical line is this. So this angle over here, is 90 minus theta, all right? And now, the horizontal axis and the vertical axis, by definition, they make a 90-degree angle. So if this is 90 minus theta, it means that this is theta, all right? This is one way for you to understand that this is always true. Eventually, you don't need to worry about proving this all the time. You just know the standard result. And every time you have a weight in a ramp pointing down and the system of axis, the referential, represented this way, you will always know that the inclination of the ramp is going to be that angle over there. And if you know this angle, and if you know the weight, you automatically know the components. The vertical component is going to be this part over here. Don't forget that when you are decomposing, you are putting these dotted lines parallel to the axis. So this is the x-axis. This needs to be parallel to these, right? So this is going to be the length of the vertical component. Same thing goes for the horizontal component. These dotted lines are going to be parallel to the y-axis, right? So this is the horizontal component. The horizontal component, as expected, is down the plane, and the vertical component is along this y-axis. So if nothing else would happen, just by the sheer analysis of the size of the arrows, what would you say? This is the only force that is, this component over here is the only force trying to pull the box down. This force is trying to pull the box up. This force is bigger than that just by looking at it. So you would say that the box was accelerating up the ramp, all right? I didn't mention one thing because I thought that it almost went without saying, but I will say this. The advantage of representing and decomposing forces is that once you decompose the force, once this weight, for example, is decomposed into the FGY and the FGX, you can forget about the weight. The advantage of decomposing forces is that when they are all decomposed in the y-axis and the x-axis, you can forget about the forces that you decomposed. Everything is going to be represented on the x-axis and on the y-axis. And everything that you need to do from that moment onwards is to analyze in terms of physics, in terms of mechanics, in terms of dynamics, to be more specific, what is happening on the y-axis and what is happening on the x-axis. So looking at this example again, once this force is decomposed, what forces you have? On the y-axis, you have the normal contact force and the vertical component of the weight. On the x-axis, you have the force F and the horizontal component of the weight. And that's it. You don't need to think about the weight, its full magnitude. Again, you just focus on its components and then you analyze what's happening. What is happening on the y-axis? On the y-axis, the box is not moving at all. Is this clear? If this is the x-axis, this is the only dimension in which the box is moving, like this. Nothing is happening vertically, all right? So if nothing is happening vertically meaning this axis, you know that this normal contact force needs to be exactly the same size, the same magnitude as the vertical component of the weight, just pointing in opposite directions so that they cancel out. There is no acceleration in the vertical component, right? So if you would add these two forces, they need to be zero. There is no acceleration, so the second law of Newton second law of Newton says that the resultant force equals the mass times acceleration, right? So if the acceleration is zero, means that the resultant force on the y-axis is zero. If the resultant force on the y-axis is zero, means that the sum of the forces on the y-axis is 0. You only have two forces on the y-axis, so the sum of this force with this force is 0. So N plus FGY equals 0, which proves that N equals minus FGY, right? See what I did here? I'm going to give more examples in the next lessons about this, but I want you to start having a perception of what is going on when we decompose forces in referentials. In the horizontal axis, what do you have? You only have two forces, and this force is bigger than that one. So again, let's apply Newton's second law to the horizontal axis only. So you have the force plus the horizontal component of the weight, Fgx, equals mass times acceleration. If the acceleration is positive, means that, and we are considering positive that way, means that this force needs to be bigger than that, right? And then it's just a matter of substituting this with the values that the question would give you, and you would calculate either the acceleration or the weight or whatever the question would ask. But more on that later. So basically, here I just represented what I just said. The resultant force in the x-axis is going to be just this minus that. The resultant force, that's what R stands for, on the y-axis is going to be this minus that. And the Fgx is going to be the weight, which is mg sine of this angle. Now look at this rectangle triangle. This is the hypotenuse. This over here is the adjacent side to this angle. And this over here, which is that, is the opposite side to this angle. So opposite side uses the sine, remember lesson 0. Adjacent uses the cosine. So the Fgx is going to be the weight, mg sine of the angle, the opposite, which is that one. This is the same as that, right? The Fgy is the adjacent side, uses the cosine. So mg, the weight, times the cosine. So this is a generic consideration about how to work with forces in 2D. So the first thing is to choose the appropriate referential, x and y axis. This shall be such that it minimizes the number of forces to be decomposed. Then decompose the forces that need to be decomposed. Everything is now represented in the x-axis and the y-axis. And from that moment onwards, you just have to analyze the motion in each axis individually and act accordingly. In a nutshell, just apply Newton's second law to each axis. All right? Next lessons, we are going to see what happens if there is no acceleration, if the forces are in equilibrium. That's next lesson. And lesson 3, we are going to see what happens if the forces are not in equilibrium, if you do have an acceleration.